The bijectivity condition for invertibility. Hello everyone. Let's begin our discussion on the conditions required for a function to have an inverse. To start, let's recall what we covered in the previous subsection. We defined an invertible function quite simply as a function that can be undone by another function. In other words, if the original function takes an input to an output, the inverse function should be able to take that output and bring us back exactly to the original input. However, it is important to realize that not every function possesses an inverse. You cannot simply assume that every mathematical relationship can be reversed. For a function to be truly invertible, it must satisfy a very specific structural condition known as bijectivity. Think of bijectivity as the golden rule that a function must follow if it wants to have an inverse. Throughout this tutorial, we are going to break this down. We will explain exactly why a function must be both 1-1, which mathematicians call injective, and onto, also known as surjective, to ensure that an inverse exists. We will examine each of these two conditions individually in the coming slides to see how they prevent ambiguity and gaps in the mapping process. Understanding the necessity of the 1-1 condition. Now that we have established that bijectivity is the essential requirement for a function to be invertible, let us examine the first part of this condition, the 1-1 property. A function, which we can call f, mapping from set x to set y, is said to be 1-1, also known as injective, if distinct elements in the domain x have distinct images in the codomain y. In simpler terms, this means that no two different inputs should ever produce the same output. To express this mathematically, we say that if the function of x1 equals the function of x2, then it must be the case that x1 is equal to x2. This ensures a strict one-to-one pairing between the two sets. But why is this specific condition necessary for invertibility? To understand this, remember that the inverse function, denoted as f inverse, operates in reverse. Its job is to take an output from set y and send it back to the original input in set x. If a function is not 1-1, it means that two different inputs, let us call them x1 and x2, both map to the same output y. If we then attempt to reverse this process, the inverse function, f inverse of y, would encounter a problem. It would not know whether to return x1 or x2. Because the fundamental definition of a function requires it to provide a single, unique output for every input, this ambiguity makes the existence of an inverse impossible. Having understood why uniqueness is required, we will now move on to the next slide to discuss the second necessary condition, the onto property. Understanding the necessity of the onto condition. Now that we have established why a function must be 1-1 to avoid ambiguity, let us move on to the second essential requirement, the onto condition. A function, which we can call f, mapping from set x to set y, is said to be onto or surjective if every single element in the codomain y is the image of at least one element from the domain x. To put this in simpler terms, for a function to be onto, its range must be exactly equal to its codomain. This means that every possible output in set y is actually reached by the function. But why is this specifically necessary for invertibility? To understand this, remember that the inverse function, denoted as f inverse, essentially reverses the original process. Consequently, the codomain y of the original function becomes the domain for the inverse function. If the original function is not onto, it means there exists some element, let us call it y, in the codomain y that was never reached by any element x in the domain x. When we attempt to find the inverse of that specific element, essentially asking f inverse of y, we find that there is no corresponding x to return to. This creates a significant problem. By definition, a function must provide a valid output for every single input in its domain. If the inverse is undefined for certain values in set y, it fails to meet the basic definition of a function. Therefore, the onto condition is non-negotiable for a function to be truly invertible. The bijectivity theorem. Now that we have explored the 1-1 and onto conditions individually, let us bring these two concepts together. When a function satisfies both of these properties, meaning it is both 1-1 and onto, we refer to it as a bijective function, which is also known as a one-to-one correspondence. This brings us to a fundamental principle known as the bijectivity theorem. The theorem states that a function f from set x to set y is invertible if and only if the function f is bijective. You might wonder why this is significant. This theorem provides us with a powerful theoretical shortcut. In many cases, attempting to algebraically derive the inverse expression and then verifying its validity can be a tedious and complex process. Instead, you can simply prove that the function is bijective. By doing so, you eliminate the guesswork. If you can successfully prove bijectivity, the existence of the inverse function is mathematically guaranteed. Real-world example, the student ID system. Now that we have established the theoretical foundation of the bijectivity theorem, let us apply these concepts to a real-world scenario to make them more intuitive. Imagine a school system where every student is assigned a unique identification number, or ID. To frame this mathematically, let us define S as the set of all students, and I as the set of all possible ID numbers. First, let us examine the 1-1 condition. If every student is assigned a unique ID, it means that no two students share the same number. This is a perfect example of a 1-1 mapping. To understand why this is necessary for invertibility, consider the alternative. If two students shared the same ID, the administration would be unable to use that ID to identify one specific student. This mirrors the ambiguity we discussed earlier, where an inverse function would not know which original input to return to. Next, let us examine the onto condition. If every ID number in the system is actually assigned to a student, meaning there are no empty or unused IDs in the active list, then the mapping is onto. If there were unused IDs, the process of looking up a student by their ID would fail for those specific numbers. Just as we saw in our previous discussion on surjectivity, this would leave the inverse process undefined for those values. In conclusion, because this mapping is both 1-1 and onto, it is a bijective mapping. Consequently, the process is invertible. This means you can move from a student to their ID, and you can perfectly reverse that process to move from an ID back to the specific student. Now that we have seen how bijectivity works in practice, let us move on to the key takeaways to solidify your understanding. Key takeaways. Now, let us move to the key takeaways to consolidate everything we have discussed so far. First, the most critical point to remember is that invertibility is equivalent to bijectivity. In other words, a function is invertible if and only if it is bijective. To understand why, let's recap the two components. The 1-1, or injective, condition is what ensures that the inverse function provides a unique output. As we discussed earlier, if a function weren't 1-1, the inverse would be ambiguous because it wouldn't know which original input to return to. Similarly, the onto, or surjective, condition ensures that the inverse is defined for every single element in the codomain. This prevents the situation we saw in our student ID example, where an unused ID would leave the inverse process with no student to point back to. Therefore, in a formal mathematical proof, if you are asked to show that a function is invertible, you must demonstrate that it is both injective and surjective. Once you have proven both, the existence of the inverse is guaranteed. Common mistakes. Now that we have explored the theoretical requirements and seen a practical example with the student ID system, let us conclude by discussing some common pitfalls. It is important to recognize these mistakes to ensure you can accurately determine if a function is invertible. First, avoid the mistake of assuming that a function is automatically invertible just because it is 1-1. Many students believe that as long as each input has a unique output, the function can be reversed. However, as we discussed in our earlier slides, this is not sufficient. If the function is not also onto, there will be elements in the codomain that are never reached. This means the inverse function would be undefined for those specific values, which violates the fundamental definition of a function. Second, be mindful not to ignore the codomain. Whether a function is considered onto depends entirely on how the codomain is defined. For instance, consider a function f, mapping the set of all real numbers to the set of all real numbers, defined by f of x equals x squared. In this scenario, the function is not onto because x squared can never result in a negative number. Therefore, the negative values in the codomain are never reached, making the function non-invertible. However, if we restrict the codomain to only include 0 and all positive real numbers, the function becomes onto, and the condition for invertibility is then met. Finally, do not confuse the two terms 1-1 and onto. To keep them distinct in your mind, remember that 1-1 deals specifically with uniqueness, ensuring that no two different inputs map to the same output. On the other hand, onto deals with coverage, ensuring that every single element in the codomain is covered by the function. By keeping these distinctions clear, you can confidently apply the bijectivity theorem to any function you encounter.